In this lecture, we'll continue our discussion about the Kalman filter. Consider a sinusoidal signal corrupted by white noise where we wish to estimate the unknown amplitude, but we know the frequency. Here would be an example. So the blue line here is the measured curve, whereas the red one is the signal without the noise. So what we want to do now is we want to estimate the unknown amplitude A given the blue measurements. To do that, we set the hidden state equal to the unknown amplitude. That will give us this state update and this C matrix. So notice that the C matrix will depend on t and will just be equal to cosine omega t, where we assume that we knew the frequency omega. The Kalman updating will be just the same as in the editing, so there's nothing we need to worry about there. We can just use the same code for that. This would be the example of the actual implementation you would use. Notice that I need to set the initial states as well as the initial covariance matrix. Here I would set the initial state to be 0. And as you can see here that the algorithm will then slowly converge, giving me an A estimate which is closer and closer to the true value. Here you can see the resulting denoise signal, where the red curve is the resulting signal using the estimated amplitude. The last figure shows the Kalman gain, and where you can see that initially we do not trust our initial state, given that we have set a relatively high covariance matrix. So I have a pretty high Kalman gain, which means that I will amplify the difference between my predicted value of the output and the actually observed output. So meaning that if my predicted value doesn't fit my observed value, I will use a strong gain to feed back to update my states. That will allow me to converge relatively fast. But as you see, as time goes by, my Kalman gain is then slowly going down to 0, meaning that I will trust my states more and more. And after a while, I will be very reluctant to update my state estimates as a result. Here's another example of an AR2. So this would be my process here. The question then would be, how should I create my states so that I estimate the A1 and A2? And I will leave that as an exercise to you. The figure shows two different cases when I set the initial noise variance to two different values. And as you can see in the first one, I have a very much noisier case, but I will react much faster. Whereas if I had a lower covariance matrix, it is not as noisy, but I am reacting slower, just as we would expect from the theory. So by selecting the initial covariance matrix RE here, we can dictate how noisy the resulting estimate should be and also how fast it should converge to any sudden changes in the parameters. I can also use the Kalman filter to do a k-step prediction. The only thing you need to do then is you need to update the states even though that you didn't have samples. So basically you make a recursion and update the states k-steps ahead by iterating those equations over and over again. In the particular case when I don't have an input, that means that I can just write it like this, and then my k-step prediction can be formed like this. Here is a result of a 5-step prediction of the Svedala data, and as you can see, I will get an MAK-1, just as I expect it to be. One needs to be a bit careful when predicting ARMA processes. Here is an example using an input as well, so this is an ARMAX. I can write it on state space form, just as we have discussed before, so my C matrix will then have this form. Notice now that my C matrix depends on the earlier residuals here. That means that if I would do a prediction, say a 2-step prediction here, my C of t plus 2 given t will depend on E of t plus 1. But of course I don't know that, so my best possible estimate of this would be 0. Furthermore, note that this depends on E of t and E of t minus 1 and so forth. I typically don't know those, so I need to replace those with estimates of the noise residual. The way I do that is that I replace these residuals by the 1-step predictions at those times, which means that I replace E of t with a 1-step prediction using data up to t minus 1 and so forth. Finally, I can also use this to predict missing samples. So say that I had outliers in my data that I removed and I want to replace them. I can then use the structure of my assumed model to predict the missing samples. To do that, I basically just update my states, and my covariance matrix is like this, but I don't have any new samples to update them with, so I'm just using my previous values. Here would be an example where all the stars are missing points, and you can see my prediction is still doing a pretty good job, clearly following the missing samples here, even though I don't have them. My prediction is good because I'm exploiting the structure of the model. It is also possible to use a forward-backward approach to interpolate this missing sample. After all, you do know these coming samples here, so you should be able to exploit those as well, and there are ways of doing that, but we will leave that for now. It's nice to see that even though I'm missing quite a few samples, my residual will still follow the MAK-1 here, so I have a good prediction residual even though I am missing quite a few samples and I had to predict those using my estimated states.